If you've ever wondered how a battery actually works, or why a nail gets rusty, or even how your own body gets energy from food, you've actually stumbled onto this secret chemical process called a redox reaction. I know it sounds super complicated, but by the end of this, you're going to see it's just a swap that literally powers our entire world. So how are we going to break this down? First, we'll get into the basic idea of what an electron exchange even is. Then I'm going to share a super simple trick involving a lion that will make this whole thing impossible to forget. After that, we'll use our new secret code to analyze a real reaction. And finally, we'll see how this is all happening in the world around you right now. All right, so to really wrap our heads around what a redox reaction is, we first have to talk about what it isn't. See, at their core, chemical reactions pretty much come in two main flavors. I know, redox totally sounds like the name of some evil alien mothership. But really, it's just a mashup of two words, reduction and oxidation. And those two ideas, they are the key to everything. Okay, so the difference is actually way simpler than you might think. On one side, you've got redox reactions, where electrons are literally traded. One atom loses them, another one snags them. Kind of like a game of chemical hot potato. Then on the other side, you've got non-redox reactions. Here, atoms just swap partners, more like rearranging the furniture in a room. Nobody's actually trading any electrons. So let's look at the first half of this two-way deal. We've got oxidation. This is the process where an element loses electrons. Now, this can feel a little backwards, I know, because you hear oxidation and you think about gaining oxygen or something. But the key, the real definition, is all about that loss of electrons. And here's the other side of that coin, reduction. This is the process where an element gains those electrons that the other one just lost. And they always happen together. You literally can't have oxidation without reduction, or reduction without oxidation. One gives, the other takes. It's a package deal. Okay, so losing is oxidation, gaining is reduction. That can totally get jumbled up in your head. But don't you worry, chemists came up with a pretty clever and honestly kind of silly trick to remember it all. It's the classic problem, right? You're looking at a bunch of letters and numbers in an equation. How do you remember which is which? Well, thankfully, there's a very famous little phrase that solves this whole problem for good. And here it is. Leo the lion says grr. This is probably the most famous mnemonic in all of chemistry, and for a really good reason. Once you hear it, you'll never, ever forget it. And here's why it's so perfect. Leo stands for loss of electrons is oxidation. Simple. And JR, that stands for gain of electrons, is reduction. It's all right there, easy, memorable, and it tells you everything you need to know. And get this, the story behind it makes it even better. A professor named Andrew Gekas apparently came up with it. The story goes he was grading this huge pile of tests, getting really frustrated, and he just started mumbling to himself, Leo says jur, Leo says jur, and, well, it stuck. He basically invented one of the most useful tricks in chemistry by accident. Okay, so we have our secret code. Now let's put it to work. It's time to go from just talking about it to actually using it to decode a real chemical reaction. We're going to use a classic example. It takes some solid magnesium, react it with oxygen gas, and you get magnesium oxide. Now on the surface, it looks pretty straightforward. But underneath, there's that secret electron trade happening. So how in the world do we keep track of this trade? Well, we use something called oxidation numbers. Just think of them as a way to keep score for each atom. The rules are pretty simple. Any pure element all by itself, like our magnesium and oxygen at the beginning, has a score of 0. When they get together and form a compound, those numbers change. And that change is the key to solving the whole puzzle. Let's track that change. Look at magnesium. It starts at 0. But in the end product, its number jumps to a positive 2. Why? Because it lost 2 negatively charged electrons, which makes its own charge more positive. That's LEO. Loss of electrons is oxidation. Now, look at oxygen. It also starts at 0, but it gains those 2 negative electrons, so its number drops to a negative 2. And that's GER. Gain of electrons is reduction. See? The puzzle is solved. Okay, so we've decoded an equation. Pretty cool. But why does any of this matter outside of a chemistry class? Well, it turns out this simple little exchange is happening all around us all the time. And this is the really big takeaway. These reactions are not just some abstract idea in a lab. They are the fundamental processes that are powering our modern world and even our own bodies. I mean, just think about it. The battery that's powering your phone right now, that's just a controlled redox reaction, pushing electrons through a circuit to make it work. That rust you see on an old car, that's the slow oxidation of iron. And maybe most importantly, every time you eat, your body uses redox reactions to break down your food and turn it into the energy that's keeping you alive right now. So when you boil it all down, it comes to this. Redox reactions are the engine of energy transfer. Without this constant back and forth of electrons, there'd be no electricity from batteries, no energy from our food, and really no life as we know it. So the next time you charge your phone, see a rusty fence, or even just take a breath, you can thank a redox reaction. And to think, it all comes back to a simple rule that some professor mumbled while grading papers. Now that you know the secret of Leo the lion, where else in your world can you spot redox hiding in plain sight?